class, we want to continue with gases. Now we want to talk about how do you collect gases. Gases are often collected over water. And in doing that, water evaporates. So there is also water vapor in the collected gases. So the partial pressure of the water vapor is called vapor pressure. And it depends on the temperature. So you can use a table to find out the partial pressure of the water vapor in the gas you collect. It doesn't depend on how much gas, how much water was in the container. It depends on the temperature. I mean the vapor pressure of the water. So if you collect a gas sample with a total pressure of 758.2 millimeters mercury at 25 degrees Celsius, the partial pressure of the water vapor will be 23.78 millimeters mercury. So the partial pressure of the dry gas itself will be this total amount, 758.2 millimeters mercury minus 23.78 millimeters mercury. And that will give you 734.4 millimeters mercury. So this is just an example of how gas is collected over water. So you have this reaction, and you see when it's zinc plus HCl. What is it going to be produced? What gas is produced there? That's your homework. But anyway, it's already here. So if you can see, this is the gas that is being produced. It's hydrogen. So it goes here, and as it goes here, it displaces water. So here you have hydrogen gas, but you have some water vapor there. So when you're carrying out this experiment, you must know the temperature in which you're carrying out the experiment so that you can know the vapor pressure of water at that temperature and be able to subtract it. So this is a table. This table shows you the vapor pressure and the temperature. So look at it. So make sure you reference this table if you have to know the pressure, the vapor pressure, to subtract it so that you can get your dry gas, the pressure of your dry gas. Okay. So let's try this example. 1.02 liters of oxygen is collected over water at 293 Kelvin with a total pressure of 755.2 millimeters mercury. Find the mass of oxygen. First of all, you have to find the pressure of the dry oxygen. So you have to go to your table, get the vapor pressure of water in this gas, subtract it. Then now you can find the number of moles of oxygen using your ideal gas equation. Then you convert the moles to mass using your molar mass. So this is what we have from the equation, from the question. We want the mass of oxygen. So this is our plan: total pressure minus the pressure of water and get the pressure of oxygen. Then you use your ideal gas equation to get the number of moles of oxygen. Then you convert it to the mass. So these are our equations that we are going to use. So you see, That's the molar mass of oxygen. This is our ideal gas equation. That's our gas constant. So we want the pressure of oxygen. So the vapor pressure from the table is 17.55, subtract it. So this is the pressure of oxygen. Then we use our ideal gas equation to find the number of moles of oxygen. But of course, you have to convert your pressure to atmosphere. So when you do that, substitute in this ideal gas equation, you get N. Our N is 4.1175. Please, three significant figures. Track your significant figures. 4.1175 times 10 to the minus 2 moles. Then you use your molar mass to find the mass of oxygen. So that is how you can collect gas over water and find the mass of the gas you collected. Now let's solve problems of reacting gases. Reaction involving gases. Let's look at how we can solve their problem. So reaction involving gases. In a reaction of gases, the amount of gas is often given in volume instead of moles. So we use the ideal gas law to convert from volume to number of moles. So when gases are at STP, we use 1 mole equals to 2.4 liters of the gas. So example, our plan can be, we move from the pressure, volume, temperature of gas A. We move from moles of gas A to moles of gas B to pressure, volume, temperature of gas B. So that's the plan. So let's take an example. What is the volume of hydrogen? What volume of hydrogen is needed to make 35.7 grams of methanol at 738 millimeters mercury and 355 Kelvin? This is the equation. You see the balance equation here? The mole ratio, we need 2 moles of hydrogen to make 1 mole of methanol. So all this is information we got from the question. That's the mass of methanol. That's the pressure, the temperature. We need the volume of oxygen in liters. So we are going to move from mass of methanol to moles of methanol to moles of hydrogen to use ideal gas equation to get the volume. So these are our equations to use to derive our conversion factors. So these are our conversion factors. This is the molar mass. This is the mole ratio from the balance equation. This is our ideal gas equation. So number of moles of methanol is 2.2284 moles per hydrogen. But to 3 significant figures, you see this line here? It shows that our answer at the end must round up to 3 significant figures. We don't do it now. Then our pressure in atmosphere, we convert it. This is it. 0.97105 atmosphere. So now we have our number of moles. Now we have our pressure in atmosphere. We want to find, here we have the number of moles of hydrogen and we have the pressure. Now we want to find the volume. Now we go to the ideal gas equation and substitute all that there. So this is our ideal gas equation. So this is the number of moles, this is the gas law, the gas constant, that's the temperature, and this is our pressure. So the volume of hydrogen needed is 66.9 liters. Let's take another example. How many grams of hydrogen is how many grams of water is formed when 1.24 liters of hydrogen react completely with oxygen at standard temperature and pressure? This is our balance equation for the reaction of hydrogen and oxygen to produce water. So the grams of water formed when 1.24 liters of hydrogen react with oxygen at standard temperature and pressure. So this information is what we got from the question. So that's the volume of hydrogen given. Standard pressure is 1 atmosphere. Standard temperature is 273 Kelvin. So we are going to move from volume of hydrogen to moles of hydrogen to moles of water to grams of water. So we have the molar mass, we have the mole ratio, and we have our molar volume at standard temperature and pressure. So you have to know that molar volume. So these are our conversion factors, don't forget. So the volume given, use the molar volume to get the number of moles of hydrogen, use the mole ratio from the balance equation to get the number of moles of water, then use the molar mass to get the mass of water. So our answer is 0.998 grams of water. So that is how we can get the mass. That is how we can do calculations when reactions occur in gases. Those are the examples. Now let's talk about kinetic molecular theory of gases. Kinetic molecular theory of gases. The particles of a gas are constantly moving. So the attraction between particles is really negligible. The particles don't attract one another. They act independently in the gaseous state. And when the moving gas particles hit another gas particle or the container, they do not stick, but they bounce off and continue moving in another direction, like a billiard ball, like a billiard ball. So there is a lot of empty space between gas particles compared to the size of the particles. A lot of space compared to the size. So the average kinetic energy of the gas particle is directly proportional to the temperature in Kelvin. So as you raise the temperature of the gas, the average speed of the particle increases. So of gases so expand to completely fill. So gases expand to completely fill their container. They take the shape of their container. They have low density. They are compressible. And mixtures of gases are always homogeneous. So why do gases behave the way they behave? Why? Why do they behave the way they do? We want to explain the property of a gas, how it explains pressure, how pressure is explained using the property of a gas. So because the gas particles are constantly moving, they strike the sides of the container with a force. The result of many particles in a gas sample exerting forces on the surface around them is a constant pressure. It produces a constant pressure. It produces pressure. So pressure is force over area. So that is how you can explain pressure based on the property of the gas. They are always moving. They strike the surface. And force over area is pressure. We want to use the property of a gas to define the fact that they have indefinite shape and indefinite volume. So because gas molecules have enough kinetic energy to overcome attraction, they keep moving around and spreading out until they fill the container. They keep moving around, spreading out. There's nothing to pull them back. There's no attractive force between the different gas particles. So they just go until they fill the container. As a result, gases take the shape and volume of the container in which they are. And that's why they're compressible. So compressibility. Because there is a lot of unoccupied space in the structure of a gas, the gas molecules can be squeezed closer together. So that's the reason. We want to use the property of a gas to explain low density of gases. Why do gases have low density? Because there is a lot of unoccupied space in the structure of a gas. Gases do not have a lot of mass in a given volume. As a result, they have low density. So that is why gases have low density. Their mass is too small compared to the space they occupy. So I want to try to use the property of a gas to explain Boyle's law. We know that Boyle's law states that the volume of a gas is inversely proportional to the pressure. So decreasing the volume forces the molecules into a smaller space. More molecules will collide with the container at any one instance, thus increasing the pressure. Thus increasing the pressure. We want to use the property of a gas to explain Charles' law. Charles' law states that the volume of a gas is directly proportional to the absolute temperature. Increasing the temperature increases their average speed, causing them to hit the wall harder and more frequently. So in order to keep the pressure constant, the volume must then increase. So that is Charles' law. The volume must then increase. Because in Charles' law, the pressure has to be constant. Now let's use property of gases to explain Avogadro's law. Avogadro's law states that the volume of a gas is directly proportional to the number of gas molecules. So increasing the number of gas molecules causes more of them to hit the wall at the same time. In order to keep the pressure constant, the volume must increase. The next that we want to use the gas property to explain the property that we want to use the gas, the law that we want to use the gas property to explain is the Dalton's law of partial pressure. Dalton's law of partial pressure states that the total pressure of a mixture of gases is the sum of the partial pressures. So kinetic molecular theory says that the gas molecules are negligibly small, and don't interact. Therefore, the molecules behave independently of each other, each gas contributing its own collision to the container with the same average kinetic energy. Since the average kinetic energy is the same, the total pressure of the collision is the same. So since the gas molecules are not striking together, each gas molecule contributes its own force to the total pressure on the side. So that is how we can use the properties of gas to explain all these laws. Now I want to talk about the kinetic energy and molecular velocities. Kinetic energy and molecular velocities. Average kinetic energy of the gas molecule depend on the average mass and the average velocity. And the equation is Ke, which is kinetic energy, average kinetic energy, equals to 1/2 mass times velocity squared. So M equals to mass, V equals to velocity, and Ke equals to kinetic energy. So gases in the same container have the same temperature, therefore they have the same average kinetic energy. If they have different masses, the only way for them to have the same kinetic energy is to have different average velocities. Lighter particles will have faster average velocity than the more massive particles. It means the lighter particles will move very fast compared to the ones which are massive. So let's examine molecular velocities. All the gas molecules in a sample can travel at different speeds. However, the distribution of speed follows a pattern we call the Boltzmann distribution. We talk about the average velocity of the molecules, but there are different ways to take this kind of average. The method of choice for our average velocity in this class is called the root mean square method, where the root mean square average velocity, URMS, is the square root of the average of the sum of the squares of all the molecules' velocity. The square root of the average of the sum of the squares of all the molecules' velocity. And this is how we write it. Root mean square. So this is sum velocity squared divided by and this is the mean. Then you take the square root. You can write it this way. So this is our Boltzmann distribution. See, fraction of molecules, molecular speed. This is how our Boltzmann distribution looks like. This is for oxygen at 300 K. So total molecular velocities. So kinetic energy, average kinetic energy equals to half times the number of moles, Avogadro's number, this is 6.022 times 10 to the 23, Avogadro's number, then mass, then root mean square velocity. So that's how we get the average. So average kinetic energy is 1.5 gas constant times temperature. So, but the gas constant this time is written in the unit of energy. So this is it. 8.314 joules per mole per Kelvin. And joules is kilogram times meter squared divided by second squared. So equating and solving, we get Avogadro's number times the mass equals to the molar mass in kilograms. This is the molar mass in kilograms. So root mean square velocity, we can write the equation this way. This is the molar mass. Arrow, this is the gas constant, this is the temperature. So as temperature increases, the average velocity increases. So molecular speed versus molar mass. Molecular speed versus molar mass. So in order to have the average kinetic energy, heavier molecules must have a slower average speed. So you can see that. Look at this lighter gas particles. See how they can speed up. See, all of them, look at their speed, molecular velocity. But when it comes to the heavier ones, you see, water molecule is water is 18. This is 28. And this is 32. So the heavier they are, their speed is slower. So this is the variation of velocity distribution based on the molar mass. So I want to look at temperature versus molar mass. As the absolute temperature increases, the average velocity increases also. The distribution function spreads out, resulting in more molecules with faster speed. So as the absolute temperature increases, so here is temperature, the average velocity increases. The distribution function spreads out, resulting in more molecules with faster speed. So you see, more molecules are with faster speed as the temperature increases. You can see that more of them are running and going compared to when the temperature was lower. So I want to calculate the root mean square velocity of oxygen at 25 degrees Celsius. So that's our temperature. This is what we want, that's the molecule. So this is our equation. Don't forget our gas constant is in joules. So we convert our temperature to Kelvin. And we substitute. So make sure you convert your molar mass to kilograms. Don't forget. Convert your molar mass to kilograms, otherwise you don't get it. So that is your answer. So we are going to continue from here. From here we are going to look at mean free path. So thank you so much for coming.